Today on Bodie Knows, we're making a custom embossed aluminum keychain on a CNC router. Let's look at the CAD design, machine setup, machining operations with feeds and speeds for you to try, Fusion 360 tips, and CAM programming. I learned a lot making these parts, and I hope you can take some knowledge away too.
Hey everyone, it's Bodie from Bodie Knows. Do you watch these videos with a cup of coffee in the morning like I do? If so, good morning. Today we're going to walk through the steps to make this custom keychain. I'm editing this video in Lake Vermilion, Minnesota. I hope you enjoy, and cheers.
Before getting going on the CAD design, I want to point out that I use a space ball, so if you're wondering how I'm rotating everything around without really using the mouse, that's how I'm doing it. A space ball looks like this. Highly recommend this. I don't know how I could possibly do my day job if I didn't have this thing, so super nice. Anyways, to get going on the CAD design, first step, just started with a block, pretty simple. I then added these numbers. So something to point out here, if you look at this sketch, to get this to fit, obviously right here these letters and numbers are too short. If you try increasing the height of them, it increases the length as well, and that's no good. Maybe there's an easier way to fix this, but obviously that's not going to work. So the way around this that I chose to use was just by using a scale function. So right here, I just did a non-uniform scale in the X direction only, and that works really nicely. After doing that, I moved all the bodies around to fit like I wanted to, so just using the move tool, put them exactly where you want. I'm a big fan of keeping bodies separate when you're doing things like this. Next small modification, sometimes these Fusion fonts come in weird with extra faces and curves that you don't need, so if you try to blend this edge right there, you can end up with problems. So I used a delete face operation right there and on the other side of this end to get rid of those faces before applying my blends. And if you don't do that, those blends can get all screwy. I then did that on the rest of the letters and numbers, added this small cutout since it's a keychain, cleaned up the outside profile, basically getting exactly what I want. So really simple design here, only a few steps. I then just used a linear pattern to get my other piece, and you're off to the races. Comment here, I don't think you'd actually need to model this second part if you just used a linear pattern on the cam side as well, but I didn't realize that until about halfway through my cam setup. To start out on the cam side of things, I modeled my stock, so that's just an extra piece of aluminum I had laying around. I think it's really helpful to actually use the stock you're going to be using. Started out with a 6mm Datron single flute 4-in-1 end mill, basing my feeds and speeds off this Datron cutting guide, although you do have to modify them a bit because they're telling you to go 40,000 RPM and some ridiculous feed rate that is just not feasible on a desktop router. But it's a good place to start. Their numbers are better designed for high-speed machining and not so much traditional machining. Anyways, this tool, we're going 24,000 RPM, 6mm step down, and 50 thou optimal load. Ended up working out pretty nicely. We'll look at it in the machining video. Facing operation just to clean up this top, make it nice and smooth. Then come in with another 3D adaptive, this time with a 3mm Datron single flute. Here we're going 24,000 RPM, but I ended up dropping this to 20,000 on the when we started machining. 25 thou optimal load and 1/8 inch step down. Forgot to mention on this first adaptive operation, I do have the shaft and holder option turned on. So when you this tool only has a 7mm flute length, so after that 6mm first cut, if you go down further, you're going to rub the side of the shaft. So I have that shaft and holder option turned on, so it automatically steps over and avoids rubbing the shaft on the stock. That works out really well. I like that feature a lot. After that, after the 3mm adaptive, we do a 3D pocket again with the 3mm Datron single flute, and that's just to get into these small pockets that the helix entry on the 3D adaptive couldn't get. I do like this ramp situation a lot. I'm not exactly sure what this is called, but I had the lead in way too high, so there's a lot of air cutting on this operation, and next time I would definitely switch things up so there's less air cutting time. Do another adaptive in this pocket, followed by a contour just to cut all the way through, so when I do the facing on the back, I have no material left. I then do a 3D adaptive with a 1/16 single flute end mill. So first cut with this guy, took it pretty slow, 14 inches a minute, I do go a full 1/8 inch step down, but only a 1/6 thou optimal load. I do another 3D adaptive here with the stock to leave turned way down so I get fully in these corners. So that's when I set, so when I come around and do this contour next, I don't run into a bunch of stock in these corners and break my end mill, and this worked pretty nicely. I used a linear pattern here just to do that same operation on the second part. As I said before, I think you could just linear pattern this entire operation and not even model the second part. It would also cut down considerably on computation time. In hindsight, I should have just done that. So again, next we do a 2D contour for all these letters and numbers with the 1/16 inch single flute. I go even slower here, only 12 inches a minute, and that now it's only taking off the stock to leave from the previous operations, which was about 5 thou. Next, you do a chamfer on all these letters and numbers here. There's only a 10 thou chamfer, super light duty, worked out pretty nicely. And then I chamfer this outside profile of the whole part. So I have it set up here so the tool comes down and comes straight in. I really like that. If you were to set this up what most people would probably consider the normal way, just by selecting this entire outside contour, you'd get a path that looks like this. It would start on the corner and round the corner as it comes in, and that gives you a chamfer that looks like this. I don't love that. I think it's kind of weird how it starts on the curve. I also think that my machine would jar around a lot if it came straight down and immediately accelerated to the left. So I would rather have all that movement happen out here and then come straight into the chamfer toolpath. So the way you can set that up is just instead of selecting that entire outside contour, only select what you want. So click again, make sure open contour is selected. Now 1, 2, 3, make sure nothing else is selected by default. So yep, right here we got to get rid of that. It'll get all wigged out if you have other parts in there that aren't part of the path you want. Do not hit OK, hit accept current contour. You need a tangential extension distance. That's just the amount, or the distance away that it starts out here before coming in. Alright, now we have what we want. Come straight down and then straight in. So any movement of the machine is going to take place out here, and by the time it actually starts cutting, you're going to be on a nice straight tool path. Your chamfer looks like this, so even though it comes straight in, that blend, kind of the round on the part gives you a nice blend by default coming in, and then same thing on the outside. Comes around. Boom, there you go. And again, I used a linear pattern here to do this. For the backside operation, we just have a single facing operation. I'm using the Datron 4-in-1 single flute 6mm end mill again here, going pretty fast, 130 inches a minute. That's 5.5 thou per tooth. Maximum step down of 60 thou, and then I change it for the finish, 10 thou step down and only 80 inches a minute for the finishing feed rate. So that 10 thou and 60 thou do not divide nicely into the distance, the total amount of material you need to remove here. So there end up being 3 different step downs. This first one's pretty light, second one is big, and then the third one is the correct 10 thou. So I'm kind of glad that it happened this way because I got to see 3 different rates. This ended up working out really nicely. It was a huge material removal rate, and we'll look at that in the video. For stock positioning, I'm using 1/8 inch dowel pins aligned with the machine y-axis. For work holding, I'm using basic clamps. I really need to get a better setup going on, but these are cheap and easy. The stock position wasn't super critical on this, as I have plenty of stock material on every side of the part. This first operation is an adaptive clearing with a 6mm Datron 4-in-1 single flute. I love these things. 24,000 RPM, 75 inches per minute, 6mm depth of cut, 50 thou optimal load. That's about a 0.9 cubic inch per minute material removal rate. Super easy for this guy. This particular end mill is really short and stubby. Very, very little chatter with it as opposed to the long 6mm I had been using before. You may notice that I have a coolant system on this machine. I'm running Cool Mist 77 mixed with distilled water through a DIY fog buster. Works really well, but does leave a sticky residue once it dries, which is kind of frustrating. I do regret my clamp placement right about now. You can see the router knocks that clamp loose. That's a very lazy mistake on my part. I did leave 20 thou radial stock to leave on this operation, so I just set it back up and hope for the best. That did end up being a problem eventually, which you'll see. Speed things up a bit here. I think you could push this end mill a lot harder. The main limiting factor is the adaptive slotting, moving the machine back and forth so fast. I just don't have the rigidity to handle that. But maybe if I took a bigger axial cut and kept the speed the same, we could up that material removal rate. I'm taking quite a bit of stock here just so my machine doesn't start rocking and rolling on these narrow adaptive tool paths. That being said, everything does look really good here, coming in and doing these small pockets, not much rocking or rolling. Check out how well those chips get evacuated by the single flute. At 24,000 RPM, they're absolutely flying, even with the sticky coolant on them. That being said, I do pop in here every so often with a blowgun to get the ones that manage to stick around. You can see this pretty well in the high speed, but let's slow it down here and show how the stock starts moving right here, which is a big bummer. So those clamps are just not set up well enough. Again, my mistake. That ended up being a slight problem further down the road, but none of the other tools were putting enough load on the material to move it around like this 6mm, so thankfully this was an isolated problem. Here's the first facing operation just to make that top nice and smooth. I'm going 130 inches per minute, which is one of the fastest operations I've done. 20 thou optimal load, 31 thou depth of cut, looking really, really nice. Also sounding very nice. You've probably already noticed this, but you can tell a lot about how well the cut is going just based on sound, and this one I really like. Next operation is an adaptive clear with a 3mm Datron single flute to get what the 6mm couldn't. This is a regular single flute from Datron, not the 4-in-1 like the 6mm. I got him just because they're a lot cheaper than the 4-in-1s, but it seems to work just as well. This is the first time I've done aluminum with the 3mm, and I'm impressed. Now I really want to try the 8mm, so be on the lookout for that video. I took the cut fairly lightly on this first one. I think we could have pushed it a bit further. 45 inches a minute, 20,000 RPM. I actually started it out at 24,000 but brought it down because it just didn't sound quite right. Optimal load of 25 thou, depth of cut 1/8 of an inch. It looks good here, everything is working well. I do have a little too much coolant on there. I usually start a new tool with a lot of coolant because I'd rather have a little extra cleanup than a broken end mill. In the end, I did turn the amount of coolant down and the chips just started flying out, no problem. Finishing off that adaptive, we go into the 3D pocket. This is the first time I've used the 3D pocket, and I did that just to get into those smaller areas where the helix entry wouldn't work. I do like this back and forth ramp, not exactly sure what that's called, but I had the lead in way too high, and man, it took forever, so I'm going to spare you and cut most of the operation out of this video. Let's look at it with a different camera view, going 55 inches a minute, 20 thou depth of cut. It's a full width cut on that 3D pocket. It went fairly well. I think you could have taken it a little faster. I definitely would mess with the settings though, because again, this is a 35-minute operation that probably could have been cut down to more like 6. I love the way how it gets into these corners here. Look at that, just boom, 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 stepping down to get into the corner. Here's how we're looking after those 3mm cuts. I like what I see so far, no major issues. Next we've got the 1/16 inch end mill. First impression, damn, this thing is small. First step is the adaptive clear to get what the 3mm couldn't. I do need to apologize for the video quality. I got a new GoPro and apparently do not have the focus situation figured out. I did get some really cool video of my dog Boo running up north though. Here's another view. Those chips look awesome. I think I did have too much coolant bogging them down, so I eventually turned the coolant off and turned the air up. After the adaptive, we went to a 2D contour with the 1/16 single flute, 20,000 RPM, only 12 inches a minute, 1/16 inch depth of cut, and then only 5 thou optimal load to get rid of the axial stock to leave from the previous operations. This looked nice and clean, but it did take a while at only 12 inches a minute and 3 steps to get down through all that Z height. Gotta run at 7.5 times speed to get us through this video. As I said, I ended up turning the coolant basically off here just to help get rid of all those chips. They do not fly out quite as nicely as they do with the 6 or the 3mm. I just want to show here how slow that 12 inches a minute is. Here's the stepper motor moving around. Tick, Talk. Finally, here's how we're looking after those 1/16 operations. The second to last set of operations is chamfering. I'm using this single flute chamfering tool that I originally got from McMaster to use on a drill, but I've been using it on the CNC after I broke my other chamfering tools. Obviously, you've gathered that I really like single flutes, and you can run this thing at 20,000 RPM. I want to show how the Z-Probe program I'm using works here. I should make a video on this. Very easy to program and customize. This chamfer looks really nice. 36 inches per minute on a 10 thou chamfer, so very little load. The machine just zips around. If you have a favorite chamfering tool, would you please let me know in the comments? I've been wanting to try a helical flute tool, but it's hard to spend like $50 when these simple tools are 10 to 15. This is a good time to mention that this material is 6061 T6 aluminum. 6061 is by far the most common wrought alloy. Contrary to what you may think, aluminum is super cheap. If you were to buy just this single piece, it would only be about $15. Here's that other chamfer that we talked about coming in straight from the side. You can see when it came down, there's a little bit of machine movement. That's what I wanted to avoid by having the tool come straight in. Get rid of all that machine jarring before the tool is engaged. And finally, the last operation is a 2D contour with tabs just to cut these guys out. So full width of cut, 3 millimeters, 20 thou depth, 45 inches per minute, 24,000 RPM. This actually ended up being pretty light. I think you could have taken a deeper cut here, but it only took a few minutes, so no big deal. You might be wondering how much air this coolant system uses. Well, kind of a lot. I have this hooked up to a 20-gallon dual-cylinder air compressor I got at Menards for $500. I used to have it hooked up to a cheap pancake compressor, but it couldn't keep up on longer cuts. Unclamp and flip it over for that second set of cuts. I didn't worry about the position of the stock too much because I was lazy, and I opted to only face the backside. In hindsight, I should have chamfered the backside too. Here's the final facing operation. 3 different cuts, all at 0.2 inch width. First at 24 thou depth and 130 inches a minute. Second pass at 60 thou depth and 130 inches per minute. That is the most aggressive cut I've made yet. It's about a 1.6 cubic inch per minute material removal rate, which is 50% higher than the numbers I gave in my last video. Last cut is 10 thou depth and 80 inches per minute. I did end up having a lot of chatter here on that second cut, not from the tool, but because there's just very little material left to hold on to these things. So what was left was moving all over the place. I slowed it down in the middle of that second cut when I heard the chatter. That's my bad for having very little material left, but it was cool to see that huge cutting rate. Ended up speeding it back for that last finishing cut, which gave a great surface finish, except the damage was already done from the second cut. You can see on the outside there that surface finish looks awesome, but the middle, not so much. When I unclamped this piece, I blew everything off with the router still on. I recommend keeping your router on when you're blowing anything with compressed air so there's positive airflow through the router. That can help prevent chips from going up inside of your router, which you definitely do not want, especially aluminum chips. I've had that happen, and it is quite shocking when the top of the router starts glowing blue from all the sparks inside. Those small little tabs just bend right off, and then you can pop these guys out. I really like that tab feature. To finish these guys off, I just took a little pliers, snipped off the tabs, then took it to an orbital sander with 80 grit sandpaper, and that worked okay. A grinder would have been a less lazy and better decision. So here's the final product. Looks good, and I'm happy with it. Spin it around here for you so you can see all the sides. Those tabs didn't quite come off as cleanly as I would have liked, but not bad. Sanded surface looks okay as well, but I would have preferred to have just left that machined. Again, a little lazy there. Front side looks awesome, except for that middle part where there are some gouges. This is where we had the machine knock that stock loose, the 6mm end mill. Then it took out a little too much material there, not that big of a deal. We do have the same situation on the other part as well. Surface finish looks okay here. I think the hobby CNC combined with the single flute end mill is just limited in the single surface finish that it can provide. Bottom surface has some swirl marks here, so those contour and pocket operations could use some settings changed up. Backside surface looks amazing, except for those huge gouges in the middle. Pretty obvious where the material bowed on that facing operation. Here's that 1/16 inch end mill up close. This is from 2L Inc. Here's the 3mm Datron single flute. Not a 4-in-1 like the 6mm, just a regular single flute. It does have an 1/8 inch shaft and a 3mm cutter. You can see here where that shoulder is and the diameter changes. Datron only sells metric tooling, but some of their small tools are available with an 1/8 inch shank, which I like because it's just one less collet reducer I have to buy. Here's that 6mm Datron single flute I love so much. Opening this up real nicely here, just practicing in case, someday Datron decides to sponsor a video. Wouldn't that be nice if I could get some of their tools for free instead of paying $70 a pop? 0068806A, 7mm flute length and 45mm total length. This is their shortest 6mm single flute. These 4-in-1s have a machine backside, so they're balanced and can run absurdly fast. They also have a wiper flat on the bottom, so you can get a nice surface finish. They run just so much better than any other tool I've been able to find. Also, the most expensive tool I've found, but worth it. Let's compare that to the long 6mm single flute that I used in my previous video. That one is their longest 6mm single flute, 0068806L. You can see this thing is much longer. It has a 31mm relieved shoulder on it and 13mm total flute length. That excess stick out does cause some chatter, all else held equal. There's a relieved shoulder that the short one doesn't have, so you can't get anywhere near as deep with the short one, but you do get a better material removal rate from the added rigidity. So in case it wasn't obvious, let's see why we had to switch up end mills big to small. That 6mm just does not get in very close, as opposed to the 1/16, which does get way in there. I actually think you could have made those radii smaller and gone further in with the 1/16 inch. Those radii are 40 thou. To wrap it up, very happy with how these turned out. Just some mild imperfections. Maybe I'm being overly critical, but in general I think this was a huge success. I'm really glad that I didn't break a single tool, even though I tried 2 new ones for the first time. Please like and subscribe to see more videos like this. Also, please do post any questions, suggestions, comments, etc. I would like to hear anyone's feedback.